Hi everyone, I am Dr. Leon Raj. In this video, I am going to explain about undamped free vibration and damped free vibration, their equations of motion and response. In the structural dynamics course, this is lecture 1. So, uh, first, idealization and assumptions. So, material assumption. These assumptions are simplifications. So assumptions means we are simplifying the physical phenomena. That simplifications include material properties such as homogeneity or isotropy. So for example, concrete is a material heterogeneous in nature, but we assume it is a homogeneous material. Sometimes the physical properties are not same in all directions. Slightly there is a deviation. Still we assume it is an isotropic material. And the materials behaviors such as linearity and elasticity. So if this is the load deflection response, if y-axis is the load and x-axis is the response, if the load deflection response is straight, then it is assumed as linear, and the loading path and the unloading path is same, then it is called elastic. Um, but actually, in reality, it will not be same. Slightly there will be a loss. So we are assuming it as a linear and elastic. Even though there is a slight deviation, then loading assumptions, some common loading assumptions are to consider the concentrated forces. So here the concentrated forces applied at a geometric point. Actually, the concentrated force means a column resting on the beam can be called as concentrated force. Actually, there is a width for the column and enough length for the beam. So it will not act on a point. So it acts over a small area. When compared to the length of the beam, the force acting area is relatively small. Hence, we call it as a concentrated or point load. Then to assume forces suddenly applied. Actually, the forces cannot be applied suddenly, but we assume that forces are suddenly applied. To assume external forces to be constant or periodic. Actually, the forces cannot be constant and periodic, but we assume it as a constant and periodic. So geometric assumptions and a general assumption for beams, frames, and trusses. So here the beams, frames, and trusses are considered is to consider these structures to be formed by unidirectional elements. So these are assumed as unidirectional elements, but actually it is a three-dimensional element which has length, breadth, and depth. But we are assuming it as unidirectional elements. Another common assumption is to assume that the some structures such as plates there are two-dimensional systems with relatively small thickness. So when compared to length and breadth, the thickness of the plate is relatively small. So we consider those slabs as two-dimensional systems. So these are the basic assumptions and idealizations. Then idealization of single degree of freedom. In structural dynamics, the number of independent coordinates necessary to specify the configuration or position of a system at any time is referred to as degrees of freedom. So single degree of freedom means only one independent coordinate is required to define the configuration or position of a system. If two degree of freedom means two independent coordinate, either it may be x or theta. So these are the uh, uh, independent coordinates required to define the configuration or position of the system. Structures can be idealized as a concentrated lumped mass M and supported by a massless structure with a stiffness K in the lateral direction. So the spring is a massless structure and the whole mass is lumped at a point, that is called lumped mass. So this system is known as spring mass system. So here the load versus deflection of three different springs A, B and C are shown here. So this is the spring and of stiffness K, and which is subjected to a displacement U, and the applied force is Fs. So applied force versus displacement is shown here. So here the spring, um, the load deflection response of the spring B is linear. This is called a linear spring. This A spring is known as hard spring and C is known as soft spring. So why it is called as hard spring and soft spring? So for a constant force, say for a constant force uh, F0, the displacement of the spring C is U2 and the displacement of the spring A is U1. So U1 for a constant force, the deflection in the spring A is smaller than the spring C. So that is why the A spring is called as hard spring and the C spring is known as soft spring. The slope is nothing but tan theta. The tan theta is equal to F by K. Sorry, F by U. So this is nothing but stiffness. So there are four kinds of problems in structural dynamics. One is damped system and undamped vibration. Another one is free and forced vibrations. So the first spring is subjected to undamped vibration and the second spring is subjected to damped vibration. And this spring is subjected to undamped vibration. So the response of the damped spring mass system is shown in this black color, and the response of the damped spring mass system is shown in blue color. Sorry, this is undamped and this is damped. So for a given time period 0 to 25 seconds, the undamped response at time 25 seconds is maximum, that is 2 units. At the same time, for the given time period t equal to 25 seconds, the damped system response is 0, tends to 0. So the reason is because of damping. So another type of problems we solved in this lecture, in the coming lectures, will be forced and free vibration. So this is a simple pendulum subjected to free vibration, and this is the vehicle moving on the undulated road. So this is nothing but a forced vibration. So for a given time period 0 to 5 seconds, and so the height of the vehicle is almost 2 meters. So what type of undulation, and how the vibration, how the mass is experiencing vibration. All these things we are going to see in the next lecture. So here we are going to see the response of undamped free vibration. A spring and mass is tied on the uh, fixed wall. So the stiffness of the spring is K, and the mass is M. Subsequently, the free body diagrams looks like this inertia force and the spring force is there. So our equations of motion is equal to mx double dot plus kx equal to 0. So mass into acceleration. So here force equal to mass into acceleration, that is equal to m into d square x by dt square. And spring force, this is inertia force, and the spring force equal to k into x. So this is the inertia force and this is the spring force. So we just take the x out, and now the equation becomes m d square by dt square plus k into x equal to 0. So divide the whole terms by m. So here d square by dt square plus k by m into x equal to 0. So either this term can be 0 or x equal to 0. Either this term can be 0 or this term can be 0. Since x is not equal to 0, since x is the displacement, that cannot be 0. The differential equation is equal to 0. That is d square by dt square plus k by m, that is equal to 0. So this is a differential equation. Hence the d by dt can be written with an operator capital D. So d square plus k by m is equal to 0. So this is like a equation. The roots for this equation d1 comma 2 are plus or minus square root of minus k by m, that is d square equal to minus k by m. So d square is equal to plus or minus square root of minus k by m. So these are the two roots, d1 and d2 are roots. The minus 1 is taken out. So these are the complex numbers. Since it is minus 1, this is complex numbers. So here natural frequency omega is equal to square root of k by m in radians per second. So basic mathematics for finding a complementary function. So if you have a differential equation, then your response is equal to complementary function plus particular integral. To write the complementary function, there are certain guidelines with respect to the roots on the characteristic equation. If d1 and d2 are the roots of the characteristic equation, and if these two values are positive, that is d1 is equal to not equal to d2, then your complementary function is equal to a e power d1t plus b e power d2t. If d1 and d2 are same for the characteristic equation, so d1 equal to d2 equal to d, and your complementary function is equal to e power a dt plus ax plus b. So when the roots d1 and d2 are complex, then you have the complex numbers that alpha plus I beta. In those cases, the complementary function is equal to e power alpha t and multiplied by a cos beta t plus b sin beta t. So this is the guidelines for writing the complementary function. So here your roots are looking like a complex numbers, that is alpha plus I beta. So subsequently the complementary function, so here x equal to complementary function plus particular integral. Here the whole particular integral is 0 and hence the response is only the complementary function. So e power alpha t into a cos beta t plus b sin beta t. Here alpha equal to 0 and beta equal to omega. Subsequently, E x equal to x is the response, and this e power 0 is equal to 1 and a cos omega t plus b sin omega t. So this is our response for the uh, undamped free vibration. So this is an assumed solution. So now it's time to check whether this assumed solution is matching with the differential equation or not. So what is your differential equation? Differential equation is equal to m d square x by dt square plus k into x equal to 0. So this is your differential equation. So the x values you are assuming. So the x value you have to substitute here and you have to check whether it is satisfying or not. So you have to find dx by dt and d square x by dt square. So the a cos omega t, if you differentiate it one time, so you will get minus a omega sin omega t. So differentiating cos, you will get minus sign. For omega t, you have to bring the omega out. So when you differentiate b sin omega t, you get b omega cos omega t. So one more time, if you differentiate minus a omega sin omega t, you get minus a omega square cos omega t, and then you differentiate b omega cos omega t, you get b omega square sin omega t. Subsequently, this is your differential equation. Check whether this equation satisfies or not. So this is your equation. Uh, so when you substitute whole term is this whole term belongs to d square x by dt square, and this whole term belongs to omega square x. So if you add this term and this term will get cancelled, and this term will get cancelled. Subsequently, this is equal to 0. Hence, the assumed solution is correct. Hence, the assumed solution is correct. Then using the boundary conditions, you have to uh, find the constants a and b. So what are all the boundary conditions? Initial displacement and initial velocity is the boundary condition. So this is the wall, and below the wall a pendulum is hanged, and if the pendulum is starting from here and you have given an initial displacement u and initial velocity v, u naught and v naught, so then the vibration starts. So to start a vibration, you have to give initial velocity, either initial velocity or initial displacement, or both needs to be given. So at time t is equal to 0, your initial velocity is equal to u0, and time t equal to 0, initial velocity is equal to v0. Your response, when you substitute t equal to 0, so substitute this in your response, you will get a cos 0 plus b sin 0. So this is 0 and this is 1, and you get a equal to u0. So you got the first coefficient, that is a equal to u0. Subsequently, for the differential of x, dx by dt minus a omega sin omega t b omega cos omega t. Instead of replacing this with v0, you will get minus a omega and this subsequent, this is to be 0 and this t should be 0, and if you substitute this, sine is 0 and cos is 1, and your v0 is equal to b omega and b equal to v0 by omega. So the constants a and b were calculated. So your response x equal to u0 plus cos omega t plus v0 by omega sin omega t. Next, using simple mathematical formulas, you have to convert this into a simplified form, or you have to find the phase angle. So the phase angle is alpha. So this is alpha angle, and the horizontal distance is u0, and the vertical distance is v0 by omega. Your hypotenuse distance is square root of u0 plus u0 square plus v0 by omega whole square. So sine alpha equal to, so tan alpha equal to opposite side by adjacent side. This is your opposite side. So this is your adjacent side. So opposite side by adjacent side is your tan alpha. Cos alpha equal to adjacent side by hypotenuse. Sin alpha equal to opposite side by hypotenuse. What is hypotenuse? Square root of u0 square plus v0 by omega whole square. Now u0 is equal to cos alpha square root of u0 square plus v0 by omega whole square. So this is your hypotenuse, and this is cos alpha. So v0 by omega is equal to sin alpha into square root of u0 square plus v0 by omega whole square. So your simple mathematical formula sin a plus b is equal to sin a cos b plus cos a sin b. So using this formula, this is your initial response, and by substituting this u0 and v0 by omega with respective equations, that this is u0 and v0 by omega, just if you substitute this and your whole term, your x response looks like this. So this is your u0 and this is your v0. Now the x response is equal to square root of u0 square plus v0 by omega whole square sin alpha cos omega t cos alpha sin omega t. So subsequently the sin omega t plus alpha. So this alpha is the phase angle. So tan alpha is the phase angle. Alpha equal to tan inverse of uh, um, v0 by omega divided by u0. So your response, this whole term is converted into a capital C, a constant C, and x of t, the response is equal to C sine omega t plus alpha. So how the response plot look like? So this is the spring mass system of spring stiffness K and mass M. The response looks like, so this is your response, y-axis is your response and x-axis your time period. So your response looks like this and it varies. So your response is C sine omega t plus alpha. Here omega is equal to square root of k by m. This is how your response looks like, because it is undamped and free vibration. Next portion of this lecture is single degree of freedom, damped and free vibration. So in damped and free vibration, the here additional damper, that is damper is provided, dashboard is provided. Your equations of motion. So this is force is inertia force, and this is stiffness force, and this is a damping force. Damping force F equal to C in the x dot. So by substituting this, you will get the expression or differential equation m into d square x by dt square plus c into dx by dt. This is acceleration, this is velocity, and this is displacement. K in the x equal to 0. So just take the x value out of all the different derivatives, and your equation is m d square by dt square plus c into d by dt plus k into x equal to 0. Your equation becomes d square by dt square plus c by m. So just we are dividing the whole term with m, c by m and k by m. So next your equation becomes d square by dt square plus c by m, d by dt plus k by m in the x equal to 0. So either this whole term can be equal to 0 or this term can be equal to 0. So of course x cannot be equal to 0. Therefore this differential term is equal to 0. So in the previous slides itself I told d by dt is the operator capital D. So capital D square plus C by M D plus K by M equal to 0. So here the response is equal to complementary function plus particular integral. Of course, there is a free vibration, so particular integral is equal to 0. Only the response is having the complementary function. So the roots of the equation is equal to minus b plus or minus b square minus 4ac divided by 2a. Here the d1 and d2 are the roots. So the d1 root is minus c by m plus square root of c by m whole square minus 4km by 2, and another root, that is another root is d2. So just simplifying this by taking the 2 inside, that is c by 2m plus 1 by 2 square root of c by m the whole square minus 4k by m, and taking the two values inside the root, and we get the d value, that is d1 as c by 2m plus square root of 1 by 4 c by 2m the whole square minus k by m. So your d1 is further simplified to minus c by 2m plus square root of c by 2m whole square minus k by m. So this is your root 1, and this is your root 2. So d1 is not equal to d2, therefore the assumed solution can be a e power d1t plus b e power d2t. So your total response is equal to just substituting this d1 and d2 value, and this is your response actually, if the roots are positive. So now there are three conditions: critically damped, overdamped, and underdamped systems. So when it is critically damped system, this whole term c by 2m whole square plus k by m equal to 0. Then c by 2m whole square is equal to k by m. C by 2m is equal to square root of k by m. Then omega is equal to square root of k by m. C by 2m equal to omega, and this c is nothing but a critically damped um, uh, c. So the roots are positive d1 and d2, that is equal to minus c by 2m. So your response is nothing but at plus b divided at plus b e power minus c by 2m t, that is c by 2m is nothing but c is nothing but ccr. So your omega square is equal to ccr by 2m. Omega equal to critically damped coefficient c by ccr divided by m, square root of ccr divided by 2m. So your critically damped system CCR is equal to 2m omega. CCR equal to 2m square root of k by m. So 2m can be split into square root of 2m and square root of 2m. Then further it is simplified to square root of 2m square root 2 into k. So that is CCR equal to 4 square root of km. So CCR equal to either 2 square root of km, that is equal to 2k by omega. So the response looks like, so here you can see that there is a uh, exponentially decaying term is there, that e power minus some constant into t. So e power minus t, that means with respect to time it slowly decays. This term, this decaying is caused due to e power minus CCR by 2m t. So your response is gradually decayed to a point. There is no vibration. So this is called critically damped vibration. Then overdamped vibration, if C by 2m the whole square minus km, if it is greater than 0, here d1 and d2 are not equal. Therefore, the assumed solution or assumed complementary function is equal to a e power d1t plus b e power d2t. So x equal to a e power d1t plus b e power d2t. Here the d1 and d2 are substituted with minus c by 2m plus square root of c by 2m whole square minus k by m, and minus c by 2m minus square root of c by 2m whole square minus k by m. So this is the response for overdamped system. Next, underdamped system. When the c by 2m whole square minus k by m is less than 0, then d1 comma 2 equal to minus c by 2m plus or minus square root of minus k by m minus c by 2m the whole square. So here the minus is taken out and the response is written like c by 2m plus or minus I square root of k by m plus c by 2m whole square. So d1 and d2 are imaginary roots, that is complex numbers. Alpha plus I beta are the complex numbers. If that is the case, then your complementary function is e power alpha t plus a cos beta t plus b sin beta t. So this is your alpha actually, and this is your beta. So uh, alpha is written as minus c by 2m into t plus, so this is your alpha and this is your beta. So beta is nothing but square root of k by m minus c by 2m whole square. So your response is equal to x equal to e power minus c by 2m a cos omega dt and plus b sin omega dt. So this is damped natural frequency. So your omega d is equal to square root of k by m minus c by 2m whole square. So omega d equal to square root of omega square minus c by 2m, and which is multiplied by the by k in the top and in the denominator, and in the numerator and denominator. So your k by m is written as omega square minus k by m is omega square. Then again here another square is this omega power 4 c by 2k whole square. So your omega d is equal to square root of omega square 1 minus omega square c by 2k whole square. So c omega divided by 2k square. So your C by 2k by omega. So this is nothing but 2k by omega is nothing but your CCR, that is critically damped coefficient. So your omega d is equal to omega is the natural frequency in the square root of C by CCR. C by CCR is nothing but damping ratio. Is nothing but a damping ratio. So C by CCR is nothing but xi. So omega d, that is damped natural frequency, is equal to natural frequency in the square root of 1 minus xi square. So for underdamped system, your assumed solution is equal to e power minus alpha t plus a cos beta t plus b sin beta t. See here, alpha and beta are nothing but, beta is nothing but omega d. Here your alpha is nothing but minus c by 2m. So just multiply this c numerator and denominator by k. Then this term is again rewritten as c by m. K by m is nothing but k by m is nothing, omega square is equal to k by m. So here is omega square. So your x equal to e power minus omega c by 2k by omega. So your response x equal to e power minus omega xi t a cos omega d dt plus b sin omega dt. So here the boundary conditions are same. When time t equal to 0, response x equal to u0. When time t equal to 0, your velocity equal to v0. Just substitute this term, e0 equal to 1, a cos this is 0, a cos 0 1, that is a, and your u0 equal to a cos 0. So a equal to u0. Next constant. So b we have to find. So for finding that, we have to find dx by dt. Dx by dt is nothing but a e power minus I omega t cos omega dt plus b e power minus omega t and sin omega t omega d dt. So here two terms are there, sin omega t. So here also t is there, and here in the cos term so t is there. So you cannot use normal methods for differential. So you have to use a UV formula method. So what is UV formula? U V dash minus V U dash. U V dash minus V U dash. So what is your U here? This is your U and this is your V. So your U V dash minus V U dash. So your U is nothing but e power minus I omega t, and V dash is nothing but cos omega dt. So just when you differentiate this, you will get omega dt. So this is rearranged here. Actually, this is your u and this is your v. So if you differentiate this, you will get this term and you will get this term here. So hence it is rearranged. So we get, this is our response actually. So when you substitute the t equal to 0, so this whole term is equal to 1, and this whole term is equal to 0, and this whole term is equal to 0, and this whole term equal to 1. So your v0 equal to minus omega xi a plus b omega d. So B into omega d equal to V0 plus omega psi U0. So your B value equal to V0 plus omega psi U0 divided by omega d. So your A and B values were calculated. So now using the simple triangle method to find the phase angle. So this is your U0 and your vertical distance is V0 plus omega psi U0 divided by omega d. So your hypotenuse is nothing but, so your hypotenuse is nothing but square root of U0 square plus V0 plus omega psi U0 divided by omega d whole square. So your response x equal to e power minus omega psi t U0 cos omega dt plus V0 plus omega psi U0 divided by omega d sin omega dt. So this whole term and this whole term we want to convert into this sine and cos terms. So your this is your response, and the response is rewritten here, and then your tan alpha equal to the opposite side divided by adjacent side. This is your opposite side. V0, this is your opposite side. This is your adjacent side. So tan alpha is equal to opposite side by adjacent side, that is V0 plus omega psi U0 divided by omega t divided by U0. So cos alpha equal to adjacent side divided by hypotenuse, and sin alpha equal to opposite side by hypotenuse. So you got tan alpha, cos alpha and sin alpha. Subsequently, you can get the values of U0 and V0 plus omega psi U0 divided by omega d. So you get the values of U0 and the V0 plus omega psi U0 divided by omega t equal to cos alpha in the square root of this hypotenuse term and sin alpha in the square root of this hypotenuse term respectively. So cos A minus B is equal to cos A cos B plus sin A sin B. So using this simple formula, so this sin alpha, so this whole term will be taken out. This cos alpha and sin alpha were substituted in the response, and you will get e power minus I omega t square root of u0 square plus v0 plus omega xi u0 divided by omega d whole square plus cos alpha cos omega dt plus sin omega dt. So this whole term can be rewritten as cos omega dt minus alpha. So this is the simple formula, mathematical formula we have used here. So your C value is equal to square root of u0 square plus v0 by omega psi u0 square plus omega t. So this is your response e power minus I omega t. So this term is e power minus omega t omega xi omega t is there. So this is the term which makes this response and tends to 0. So you can see the response here. So the u0 is the initial displacement, y-axis is the displacement, x-axis is the time period, and this uh, completes one cycle. So this whole this one vibration is the time period td. So mid of these things nothing but td by 2. So the another vibration is completed, another 2d. Damped time period. So why it is called td? So this is nothing but damped time period. So damped time period is nothing but 2 pi by omega d. So Td equal to 2 pi by omega in the square root of 1 minus psi square. So next important part is deriving the logarithmic decrement. So we got the response that if the response is x1, then the time period equal to e power minus omega psi t1 c cos omega d t1 minus alpha. So here cos omega d t1 minus alpha equal to 1, and your response x1 equal to e power minus omega psi t1, and x2 is equal to c into e power minus omega psi into t1 plus td. This is a damped time period. So in this case, x1 divided by x2 is nothing but your c get cancelled, and e power minus omega psi t1 and e power minus omega psi t1 plus td. So on the both sides, if you take logarithmic values, so ln of x1 divided by x2 is equal to ln of e power minus omega psi t1 divided by e power minus omega psi t1 plus td. So in logarithmic values, you can just instead of dividing it, you can subtracting the logarithmic values. So subsequently, ln of e power minus omega psi omega t1 minus ln of e power minus omega psi omega t1 plus td, and logarithmic and e value get cancelled, and you will get the exponential terms alone, and just subtract these values and you will get xi omega td. So td is nothing but 2 pi by omega d. So this value is nothing but omega d. It is damped natural frequency for small values of psi. So your logarithmic decrement is nothing but 2 psi omega. So in the next class, we are going to see the forced vibration, uh, displacement transmissibility, and force transmissibility. So these are the reference books: Dynamics of Structures by Anil K. Chopra, Structural Dynamics by Professor Maria Pos, Shom's Mechanical Vibrations. So these are all the books I referred, and thank you.